In this section, we'll learn about eigenvectors and eigenvalues. So we've been talking a lot about the linear transformation done by a matrix W. Here I'm showing a bunch of different vectors before the transformation and then after the transformation. And these vectors most of them are changing direction and length. They're sort of warping along an axis. But you might notice that two of the vectors, G and C, aren't changing direction. These are eigenvectors of the matrix W. And eigenvectors of a matrix are just that, vectors that don't change direction when multiplied by that matrix. They can change length though, so here C and G are still eigenvectors, even though they're getting longer. And each eigenvector has an associated eigenvalue, and the eigenvalue tells you how much the eigenvectors change length. Basically, the eigenvalue is the scalar multiple that changes the vector. I wasn't completely correct earlier when I said that eigenvectors don't change direction, because they can flip to the opposite direction. And in that case, the eigenvalue would be negative, and negative scalar multiple flips the vector. So here you can see that C and G swap directions, but they're still eigenvectors. And so eigenvectors are really vectors that, when multiplied by a matrix, W, are equal to some scalar multiple, the eigenvalue, of themselves. And so basically, with eigenvectors, they're just changing along their span. So in this case, it would be along this one-dimensional line. I also want to note that I've been talking about C and G as eigenvectors of a matrix, but every single point along this one-dimensional line is also an eigenvector. So basically, everything on this line is an eigenvector, so there's kind of an infinite number of eigenvectors for this matrix. They just all fall along that line. So in that case, we normally just pick one of them, pick one eigenvector. And helpfully, importantly, all of the eigenvectors along one line would have the same eigenvalue. So we can just summarize by picking a vector along that line. And we usually pick a unit vector. I'm not going to go through how we actually compute eigenvalues and eigenvectors because it's a little more in depth than I want to go. But we do want to know why we care about this, because coming in, I think it seems like somewhat of an arbitrary concept. Why do we care about particular vectors that aren't knocked off their span? And the first reason we care is that eigenvectors are a really good way of figuring out what the transformation is that's happening. And you'll see that in the exercise you're about to do. A second reason we might care is that eigenvectors and eigenvalues are extremely important for understanding dynamical systems. You'll see this later in the course when we talk about linear dynamical systems. But there's also a bonus tutorial for this day where you will be looking at a discrete dynamical system and how the eigenvectors can inform you as to what's happening. So now you are going to identify what transformation is happening from the eigenvector. So before, you thought about where basis vectors ended up to think about transformations, and now you'll think about what happens to the eigenvectors.